In this video, we are going to work through a practice problem that involves rotational kinetic energy. So let's jump right into this example. It says, a solid cylinder with mass 0.75 kilograms and a radius of 2 centimeters starts from rest and rolls down a 2-meter high incline. Calculate the speed of the cylinder when it reaches the bottom of the incline. So I've sketched out this situation. We have this 2-meter tall incline, and we have this solid cylinder that is rolling down the incline. And we want to know when it reaches the bottom of the incline, what will its speed be, or what will its velocity be? So to solve this type of problem, what we need to recognize is that the only force at work here is gravity. So gravity is what's causing the cylinder to roll down the incline. And gravity is known as a conservative force. So when we only have conservative forces at work, it means we will have a situation where we have conservation of energy. And that says that the mechanical energy, the initial mechanical energy, must be equal to the final mechanical energy. Now, mechanical energy, that's just the sum of the potential energy and the kinetic energy of an object. So for this example, our initial mechanical energy, notice that this cylinder, due to its height at the top of the incline, it has potential energy, but we're told that it starts from rest. So initially it has no kinetic energy. So what we can say is that the initial mechanical energy, it's just all potential energy. And that must be equal to the final mechanical energy. So once the cylinder actually reaches the bottom of the incline, it no longer has potential energy since it has no height associated with it, but it does have kinetic energy. And it turns out there are two types of kinetic energy that it has. The first is it has something known as translational kinetic energy. And that's just the kinetic energy associated with the movement down the incline. And it also has rotational kinetic energy. And that is the kinetic energy due to its rotating movement down the incline. Or in other words, as it rolls, it has rotational kinetic energy. So this is the equation that we're going to use to solve this problem. So let's go ahead and fill in the formulas we know. Potential energy, that's calculated as mass times the magnitude of gravity times height. And that's equal to translational kinetic energy, that's calculated as 1/2 times the mass of the object times the velocity squared, plus the rotational kinetic energy, that's calculated as 1/2 times I, the moment of inertia, times omega squared. Now, for this example, we're told that we have a solid cylinder. So the moment of inertia, the formula that you'll use for this, it depends on the shape of this object. So for a solid cylinder, the moment of inertia, I, that's calculated as 1/2 times the mass times the radius squared. So it's really important that you use the correct moment of inertia formula. If this was, let's say, a solid sphere instead, this formula would be different. It would actually be 2/5 times the mass times the radius squared. So depending on the shape of the object, make sure that you're using the right moment of inertia formula. So let's go ahead and fill that in for I. So what we'll get is mgh is equal to 1/2 mv squared plus 1/2. For I, we have 1/2 times m times the radius squared. Now, for the angular velocity, we also need to know another important formula here, and that is the angular velocity of an object is equal to the linear velocity v divided by r, the radius. So what we can do is we can substitute this value in for this angular velocity here. And notice that we have squared. So really what we're substituting is v squared over r squared. Now, one thing we'll notice is that when we make this substitution, the r squareds actually cancel out. So the radius actually doesn't matter. And so this simplifies to mgh is equal to 1/2 mv squared plus, here we have 1/2 times 1/2, that's 1/4, times m times velocity squared. So once we get to this formula, we're trying to solve for v, the velocity. So one thing we'll notice is that all of the terms have an m, the mass, so those will all just cancel out. So the mass of the object actually doesn't matter either. So what we end up with is gh must be equal to, we have 1/2 v squared plus 1/4 v squared. So 1/2 plus 1/4, that's equal to 3/4. And then we have v squared. So to solve for v, the velocity, we can multiply both sides by 4/3, so that will cancel out this 3/4. So here's what we get. V squared is equal to 4/3 gh. And to solve for v, we can just take the square root of both sides. So what we'll find is that the velocity is going to be equal to the square root of 4/3 times the magnitude of gravity times h, the height. So to find our final answer, we're just going to substitute the magnitude of gravity, that's 9.8 meters per second squared, and we'll substitute in for h, that's the height of the incline, which is 2 meters. So let's clear a little bit of space right here and write our final answer. Okay, so for our final answer, we get v is equal to the square root of 4/3 times the magnitude of gravity, we said is 9.8, and the height is 2 meters. So when you punch this into a calculator, this comes out to about 5.11. And we're talking about velocity, so our units will be meters per second. So that is what the velocity of this cylinder will be once it reaches the bottom of the incline.